It's really great to be here. I get to talk about probably the thing I like most in the world, which is great, although maybe that doesn't say very great things about me, that I like this so much. Notice I'm using this particular word, advanced computing. This is something I've taken to fairly recently, where I feel like high-performance computing has this connotation of, well, you're only, if you're not using 20,000 nodes of a supercomputer, you're not doing high-performance computing. I sort of disagree with that philosophy, and I think there's a lot of really interesting, cool stuff that doesn't need 20,000 nodes of a supercomputer, but still is not run-of-the-mill computing. And so a lot of what I'm going to talk about falls under this umbrella that I'm calling advanced computing. And for the interest of time, we're going to power through some of these slides. This is some of the stuff that I do on the internet. You can find out all about me. I have some blogs, and I write a bunch of code. Sometimes I post jokes on Twitter that people don't think are funny. So a quick introduction. Talk a little bit about Exceed, which is the organization that is covering my time to be here today. And they offer some great services. Big data as I understand, it relates to biology. And then just a quick discussion of why code might be slow. So what is Exceed? Exceed is this horrible acronym, Extreme Science and Engineering Discovery Environment. Not that punchy, but it's a really great organization. So it's a cyber infrastructure organization run by the NSF. So if you have an appointment somewhere at some kind of American institution, a national lab, you're all students. So if you're a student at a university in the United States, then you are eligible to work on Exceed resources. So the way it works is we have centers, like the one that I work at, and those centers stand up computational resources, supercomputers, increasingly things that are advanced computing, but not really supercomputers, cloud computing kinds of environments, for example. So centers stand those things up, and Exceed connects researchers to those resources. And so you can get an allocation on these resources for free, and you'll get something like 50,000 service units. A service unit is a compute hour. So if you're running a serial job on one core, you get 50,000 hours on one of these machines, right? Pretty nice. So getting an allocation, there are different kinds of allocations. At your career stage, probably you'd want to think about a startup. One of the nice things about a startup is it's a rubber stamp. So you say, I have this problem, it's such and such biology something, and I think I could use such and such resource. If you want to know what resource might fit your problem, and I'll make these slides available to you at some point. So there's lots of clickable links you can follow eventually. But you have some kind of computational problem, you need some amount of bigger hardware, or maybe even consulting services to help you solve that problem computationally. Exceed offers these kinds of services. It's all free. Well, paid for by taxes, if you can call that free. So you can see your campus champion if you have one at your university. These are also great folks to engage with, to get plugged into the Exceed community. And here's the different kinds of allocations you can get. Again, probably you'd want to think about a startup. You write very little. It's the easiest proposal you'll ever write. And then boom, within a week or two, you're going to be up on these huge resources. So it's a really great service. And they have all kinds of training available. They're working on developing some MOOC-like certifications. I always view these things with suspicion, like they're a bit of a scam, but if you want them, they'll give them to you. So there's all kinds of training. They have exabytes of storage available, all kinds of research software available on these machines. If they don't have what you want, they can generally install it. So that's the sales pitch for Exceed. If you have questions, sure, yeah. So that's unfortunately kind of a complicated question. It is NSF funded, and so, oh, that's right. So, what's the timeline? What's the scope and availability and these kinds of things? Exceed itself is up for a 5-year renewal, so it has at least one more year of existence, and then possibly 5 more, and we're optimistic we'll get 5 more. But Exceed doesn't actually own any machines. So, we at University of Tennessee have some machines that we give amounts of them to Exceed. And Exceed allocates those to researchers. So it's a little complicated. So if you have specific questions about Exceed or how any of that works, I'd love to talk to you. So Big data in biology. Big data, they use these words, volume, velocity, and variety. So I'm not a biologist. My background is math, computer science. So trying to fit my perceptions of biology may be slightly off, or I may only see one facet, whereas you're working in a completely different environment. But they use these terms, volume, velocity, variety. So volume, you have these big machines, you punch a button and a bunch of data tumbles out, right? These big magic machines. This is a volume problem because the amount of data coming out of these things is growing. So you have these vast expanses of data. Maybe traditionally you have fit models on data that's in memory on your machine, and now you just don't have enough memory on your machine. Exceed can help with that, maybe. But there are other approaches, and so now you have to think about how am I even going to just get the job done? There's so much stuff. Velocity, I think, is really less of a problem in biology. Would love to be corrected. But by velocity, we mean, for example, say you're dealing with some stock market data, right? And they have like microtransaction level data. Just really, really quickly, this information is coming in. They want to build a predictive model and ship it out the door as fast as possible, right? I don't think there are too many. Maybe there's some kind of sensor application or something in biology. I don't really know. Would love to hear if there is. But I think that's less of an issue. Variety, on the other hand, is a huge issue, where you've got data coming in from all these crazy sources. Here are some basic ones. Maybe the machine has its own special crazy format, and now you have to combine all of this stuff. How are you going to do it? This is a hard workflow problem. The other issue is complexity. So, fitting like a log transform of a variable is not computationally expensive. And you can basically do this without bringing all of the data into memory. Whereas if you want to do something like principal components analysis, this is much harder. And this is just mathematically harder to do. And so if you have more data, it's going to take more computing to get the job done. Some problems that I have seen working with biologists, P greater than N, or maybe in a little more civilized language, you're working with tabular data, right? And you've got way more columns than you've got rows. For some reason, this always shows up whenever I plug in with biologists, and it may just be who I talk to. But these kinds of problems, traditional statistical methods, many of them just don't work well, right? Even just basic linear regression, or probably you would think more along like a Poisson regression maybe in biology, they just don't work as well. There are hard math problems where just things sort of break down. One of the things that I see very commonly is many, many, many small tasks. So I recently met with a researcher in biology who's getting plugged into Exceed, and she said her individual problems are very simple, but she's got like 1 million of them, and she doesn't know how to wrangle it all and get it into a final form that she can understand. This is a workflow problem, right? And you could, this is, in a sense, this is a good problem to have, in some respects anyway, because we can just fire off all those different tasks wherever on any kind of machine, multiple cores, whatever, multiple nodes. But getting all of that information into something that you can understand is a little trickier. Another problem that I've seen is that parallelization can be very difficult. So what do I mean? Maybe mathematically something splits at the amino acid level, or maybe not. And now you're just working across genomes or something. And maybe you're only interested in a couple of genomes, right? So how much hardware can you throw at the problem? This may be difficult. This may be very difficult. So these are the kinds of computational barriers that I have seen. There are certainly more. Why would your code be slow? So these are just a few, I think, of the heavy hitters. Bad code, abstraction, or maybe it's serial, it's not parallel. What do I mean by bad code? We're going to be talking about R, so hopefully we have at least some interest in R. R is not very smart, and we will touch on this in depth in the next section, but R is not very smart. If you tell it to do something, it's going to do that, and not maybe something more efficient, right? Whereas a C compiler will do these kinds of things. R will not. R is slow, but bad programmers are slower. So what I mean by that generally is, there's always 20 ways to do any one thing in R. 19 of them are terrible ideas, right? So R has this added level of complication where, you've got to know to call this function with this argument, in this way, and then it'll be fast, or reasonably fast. Another point that I like to hit home, parallelism in R is very cheap. It's very easy. Parallelism in R is easier than it is in Python, without question. I would argue it's easier than it is in Julia, a language that I like a lot. But parallelism in R is very cheap. It's very cheap in the sense of it's almost trivial to do. But if your first thought is to go parallel before you fix all of the problems, it may be faster, but maybe you spend a little more time and make it even faster than you could have possibly made it by going parallel. Just some issues that come up. Abstraction is never completely free. Anybody who tells you otherwise is a liar. Computers hate abstraction. They hate it. They don't think the way that we think, right? Abstraction could cost you like a microsecond, and maybe that's irrelevant to you. You couldn't possibly care less, or much, much, much more. Okay? Sure.
Wait, can you tell us what abstraction is?
So abstraction, thinking in the sense of, like R is an abstraction over the way the hardware really operates. Okay? When you create a data frame or a vector, these are not things the hardware actually understands. Somebody had to go define what these things are and then implement it in a kind of crummy language like C, which is closer to the way the hardware thinks. And then you just have this much easier way of translating like a math or a biology idea into something the computer can handle. So I really just mean when we work with programming languages, that's not at all how the machine is actually operating, right? And that cost allows us, or rather that abstraction layer allows us to do things we could never do if we sat around writing assembly all day, right? At the same time, it's not free. And abstraction is great. We love it. We would not be where we are today without very high-level programming languages. I love R. I don't want to get rid of R. But there are some things that R does very badly where you might want to plug into a language like C or C++. And we'll talk a little bit about C++ plugging into R. But you have to find a balance, right? There's no reason to dive into assembly or machine code or something when your problem is going to run in half a second with some high-level R code. So this is just a point I want to make. I love this picture. It's not mine. It was available here. And it starts at 1980, goes to about 2011. In fact, the picture is basically at both ends, is basically the same if you go out farther. What are we looking at? These are millions of instructions per second so we're going by year, and we're looking at millions of instructions per second. What your computer is able to compute. Or one facet of what could be called like the speed of a computer, right? And now notice, it's basically linear until you get about right here, and then it's just dead flat. And that's still true, actually, all the way to today. And it doesn't look like it's changing. So there was a time, this is one of my favorite facts, there was a time in the 1990s where if you had 1 year to solve a computational research problem, if you had 1 year, you were literally better off waiting 6 months to even start, buy your hardware 6 months later, than if you started on day one, literally. So the cheap hardware gains, or at least one facet of them, are basically dead at the moment. Okay, why am I bringing this up? The old model of we'll just have better serial code. Well, eventually you're going to push that to the limit, and then what? Your computer, one aspect of it is not getting any faster. What are you going to do? If it's taking you 2 weeks to solve a problem you need in 2 days, what are you going to do? An answer to this problem is parallelism, and we'll talk about that. So before we get into those, I want to talk about profiling and benchmarking. So these are some tools that I could not live without in the world of R. They're so super duper important, and I find a lot of people have never heard of them. So I want to plug them as much as I can. First of all, why would you profile? Here's a great picture, a great quote from Linus Torvalds with a picture of him looking very smug. He says, sometimes pi equals 3.14 is infinitely faster than the correct answer, and the difference between correct and the wrong answer is meaningless, where this value of correctness is irrelevant because it just doesn't matter. Performance almost always matters. That's really my mantra. And it's something that I think people should take a little more seriously, at least. I detest the fact that people so often dismiss performance concerns so readily. And the R community has been in that mantra for a very long time. That's changing, and I'm very happy. But, performance matters. You can't just throw all the data away, who cares? The problem's good enough, right? Well, maybe it's not. So, why profile? Performance matters. Your bad practices scale up when you think about going from serial to parallel. Your bottlenecks may surprise you, okay? You may think, oh, I'm sure this is, and when I consult with people, they say, I'm sure this is the problem right here. You profile, often they're not right. Sure. So by profiling, I mean performance analysis. I want to figure out what's slow, okay? So you've got some code, you hand to me, and you say, why is this slow? Profiling is going to allow us to answer that question. Thanks. Again, R is dumb, and R users claim to be data people, so act like it, right? This is data about what you're working on that you can generate for free and understand what you're doing, so why not get it? It's free. It's just there. So here's what I mean when I say R is dumb. Quick example. Here is some C code. We don't have to know C. All we have to know is that here's some C code. Here's the generated by the compiler. Here's the generated assembly when I compile without optimization. And here's the generated assembly when I compile with optimization. These are all instructions to the computer, okay? This is doing a lot less. Why? Because this is a stupid loop. I say for I equals 0, so from 0 to 10, I want to set this integer value x to 1. So when I compile without optimization, it's just going to do that. And when I compile with optimization, the compiler will realize that, well, I don't need to set x to 1 10 times. I can just do it once and be done. And in fact, this may have even pulled x out of the whole thing because I never used it. I never even used the value of x. So it may have just thrown the whole thing away. R will do things like this, not things like this. R is dumb. Here's a bit of a mock example. These are the kinds, this is not based on anything real, but these are the kinds of things that I see in my consulting work, where you have something like, we have some matrix A, and we're going to store the value TA is the transpose of A, and then we're going to do some computing. Now notice I never update A, right? Inside this loop here, I never update A. Yet each time in this loop, R will update TA. It'll compute that transpose, which is not cheap. And so what it'll do is, it will look at TA exists, I'm going to replace it with something, so we're going to throw that memory away. We're going to allocate the new stuff, we're going to fill it, and then proceed. So those are expensive operations that we don't need to do. It would be better to do something like this. R won't do this for you, because R is dumb. Here's a real example. One day I was looking for some examples on the CRAN, this repository of R packages. I was looking on the CRAN for some clustering applications in biology. And I found one, I thought it looked really neat. I ran their example code, and it was really, really slow. And so I looked at how big their data was that they were shipping with the package. It was tiny. It was itsy bitsy. I knew something was wrong. So I ran this through the profiler that I'm about to show you. And as soon as I did, I instantly saw the problem, went to the code, looked at it, and I saw this. I saw this as matrix call inside of this loop, right? And as it turns out, this X object was like a distance matrix. Not really a matrix, it's some special thing in R. And this as matrix cast is kind of expensive. It's like this problem here. Maybe just there's a little more context juggling around here, a little harder to understand, but it's the basic idea that we saw here. So if instead you just do that once up front, you can make this 350% faster. I did this in like 10 minutes, right? I wrote him an email about it. He didn't seem to care, so whatever. It's still slow. But, it was only 10 minutes of my time, so that's fine. So R is slow, bad programmers are slower, and R can't fix bad programming. These are very important things to keep in mind. So how would you profile R code? Here are some basic ways. Okay? If you've worked with R, you've probably seen system.time. This is a way you just you wrap it around like a function execution or some line of code or something, and it'll just tell you how long that single execution took. Right? It's a very useful tool. Much more useful, however, is rprof. How many have used rprof before? A couple, right? Next time somebody asks you that, your hand better go up, because this thing is great. This thing is awesome. There's also rprof-mem, which is a little more complicated. We won't get into that, but it exists. You might want to be aware of it, especially if your bottlenecks are memory bound. So you're just running out of memory constantly. How would you know that? I guess it would depend on your operating system, so see me if you feel that's your problem. Then there's also tracemem, which is a little less useful today, but tracemem is a way to detect if an unneeded copy, basically, of an object was created. It's a little more advanced, but these exist. You might want to be aware of them. How does system.time work? So you've got some matrix here. It's got 20,000 columns, 750 rows, and I compute transpose x times x as matrices. We can time it, and it took that much time. There's also this function crossprod, so that's significantly faster. It does the exact same thing. Yet another one of these gotchas, these mini gotchas in R where you just sort of have to know about something. But these do the exact same mathematical operation. This is just significantly faster. And basically, it's just doing half the work because it's a symmetric operation. Covariance is a related operation, but notice there's significantly more going on here. Okay? So just examples. How do you use system.time? You can also time blocks of expression where you say system.time open paren and then a brace, bunch of stuff, brace, close paren, and then you can just time whatever, all of that stuff you want to put in there, and this is nothing of interest, maybe, but just as an example, you can do that as well. But rather than going to this, probably what you really want is rprof. So rprof is great. Rprof is the R profiler, okay? And it has all of these options, many of them you may never care about. But, you know, profiling, what does it do? It's going to profile the execution of every single R function, okay? So you call some R function, and it's calling 100 other R functions vicariously. And you want to know which one of those is eating up all your time. With system.time, you can only know how long the whole thing took. With rprof, you'll know how long each component takes, or the expensive ones anyway. How does it work? It does this thing called stack sampling. So every interval, I think seconds, so 0.02 seconds, I think it's the unit is seconds, it samples the stack. What does that mean? Ask me, and I can let you know. But the nice thing about it is that you know, there's sort of this hard problem in profiling where whenever you try to measure something, you know, you're going to change it, right? You're probably very familiar with this concept. The same is true in profiling. Stack sampling is actually a really clever way to avoid this problem computationally. So it works very well. It's really nice. Here's an example. We have this matrix. It's got 10,000 rows, 250 columns. And we're going to run principal components and profile it. How do we do so? We call rprof stuff, whatever I want to profile, and then I'll call rprof null. This says start, this says stop. Okay? You can also add, if we look back here, you can also add a file name. So you want to store the outputs somewhere. They're kind of hard to read, but you want to store those outputs somewhere. You can. The easiest way to look at those outputs is to run summary rprof. Summary rprof is just going to give you a little summary. And it's going to look like that. So what do we see? Remember, we're running principal components, brcomp. So the top thing here, so it shows you two different views, by self and by total. By self, we see LASVD, so it's doing a singular value decomposition. There's a matrix multiplication in there. It's projecting the matrix onto the right singular vectors, if you're familiar with principal components. There's some allocators here. Sweep is called to like center the data, scale the data, these kinds of things. And so it's showing you all these different R functions, how much time they're taking up. Okay? And then this is just a different perspective. So of the total time was 0.98 seconds. I suspected seconds. Principal components took up the whole thing, right? prcont.default, if you know how R does its object-oriented stuff, this is just a little thing that's going to call this, basically. So that's taking up all the time. SVD takes up 0.76 seconds, and so on. Very, very, very powerful tool. Now, what if you change that interval? This ran in 0.98 seconds. And I worked very hard to get an example that would work just right in this way. If I set the interval to 0.99, what's going to show up? So we're going to do the exact same thing, except I say the interval is 0.99. The interval is the sampling interval. Okay? What shows up? Nothing. Okay? Didn't capture anything. Everything was outside of my window that I cared about. Okay? So that's a quick example of how to use RProf. There's some stuff on advanced profiling. Yeah. Mm-hmm. So that's a good question. The question was, how would I know how to set the interval? In reality, you can probably just set it to the default. If, when you run summary RProf, this thing is just swarming you with things taking up itsy-bitsy amounts of time, you might increase it to like 0.1 or something. I don't know that I would ever honestly want to go this high. This is just basically for demonstration. That's a great question. We have some advanced R profiling stuff. In the interest of time, we'll skip over this. Benchmarking. Quick discussion on benchmarking. So R functions are really complicated. Okay? Every time you execute an R function, all kinds of crazy things happen. There's a symbol lookup. There's this thing called abstract syntax tree, AST, that has to get created. There's these things in R called promises. They have to get forced, whatever that means. There's argument checking. You create an environment for the function to run in. All these crazy things happen. This is that abstraction I'm talking about. So it's really complicated. And sometimes, when you execute a function a second time, it'll run significantly faster than it did the first time. You've probably seen that if you've ever worked with R. So if you want to benchmark something, if you really want to understand, is this new method that I have really faster than this old method that we have, you have to take a little bit of care. The way I recommend doing this is with a package called rbenchmark or microbenchmark. There's a different one. rbenchmark I kind of like. So here, again, we have some simple operation comparing two different ways of computing cross product of a matrix. If I say, assuming I've installed the package, library benchmark these two functions, I can specify what columns of the output I want, having known what those columns look like, just to make it print a little nicer. And here we see that it's going to run this 100 times. You can change that in the function argument. The total elapsed time here is 13 seconds. Total elapsed time here is almost 4 seconds. But then it shows you the relative time. So if this is 1, this is 3.5. Very nice. And this is the kind of thing you could cook up yourself, but why bother? Somebody already did a really good job. There's another tool called microbenchmark, which is very similar, but it kind of has a different philosophy. And by default, it gives you microseconds, which for R I think is stupid, but whatever. You can get different units. And so you could microbenchmark FG unit equals S, and you see you get a lot more information here than you did with rbenchmark. How much of it is useful? I don't know, it depends on what your question is. Microbenchmark does have some nice plots, though. So you store that microbenchmark output and say box plot, and you'll get some box plots. It's pretty nice. So they both do similar things. They have slightly different philosophies. That's that. Okay. So very hasty introduction to advanced computing with R, what I'm calling advanced computing. You have these different ways to make stuff faster. And we're going to hit the highlights, again, in the interest of time. I think things are running a little behind. We're going to try to catch up here. So you have free improvements. You can write better code, go to compiled code, or go parallel. So free improvements. You can compile R with a different compiler. Okay? If you go download R from the R project, then probably it was compiled with, if you're on Mac, it was compiled with Clang. If you're on Windows, it was compiled with MinGW. If you're on Linux, you build it yourself probably, or you get it from a repo or something. But it was probably not built with the Intel compilers. Okay? these compilers will just make every single thing you run in R slightly faster. How much? Depends. I've heard, some people get average 20%. I have some experience with this, but the licensing rules about what I can and can't say are kind of strange, so I'll just leave that vague. But it will be faster. I can say that. It's not entirely painless, especially with these commercial compilers. R was not designed with them in mind, and vice versa. They're not free generally, as in price, so may cost a lot of money. If you're on an Exceed resource, somebody's already taken care of this for you, just to plug that. If you want to do this yourself, if you have some kind of community cluster, this is an invaluable resource that you will need to look at frequently. There's a bytecode compiler in R. What is bytecode? Bytecode is sort of like machine code for interpreters. So it's going to make certain of those things where I said functions are really complicated. It's going to make some of those things a little easier for R to do. So the bytecode compiler is a package. As of R 2.14, it ships with R. You just get it. Then as of maybe 2.15.2, packages by default, like the stats package, the base package, the packages that ship with R are compiled with the compiler, the bytecode compiler. How does it work? You can compile any function you like by calling library compiler. Library compiler. We have some function f. I'm going to say cmpfun, compile the function. And then I don't have to give it a new name. I could replace it. It's still R. All the rules are the same. But I'm going to call it something different, compare the speeds. And this was a problem I designed to make the compiler look good. When I did that, we get about 10% speed up. Not great. It's free. You don't have to work hard. It's free, but it's not great. And these could be basically, the difference could be completely, it would be exactly the same in many cases. So it's free, free speed up. You don't have to change your code. You just have to compile it once and then you're done, but it's not great. Choice of BLAS library, on the other hand, can make significant differences. So if you're doing any kind of modeling, if you're doing matrix operations, linear models, generalized linear models, principal components, more directly, if you're inverting a matrix for some kind of clustering operation maybe, or forming a covariance matrix, all these kinds of things use this stuff called the BLAS, basic linear algebra subprograms. The BLAS that ship with R are slow. They're called the reference BLAS. And you have to sort of go out of your way to use these faster ones. There's one called Atlas, and there's one called OpenBLAS. These are both free. Atlas is serial. OpenBLAS can actually use multiple threads, multiple cores of your computer. So just as an example here, matrix multiplies. You see this is runtime. Smaller is better. The BLAS that ships with R is very slow. Atlas is much faster. OpenBLAS is faster still and can go parallel. So this is one core of OpenBLAS. This is two cores of OpenBLAS. Okay. There are even commercial versions of the BLAS. Intel sells one. AMD has one. And if you have AMD hardware, the AMD one will be really fast. CUDA, if you're using GPUs, they have their own. So these are, this is just free speed up forever if you're doing linear algebra. If you're not, this doesn't help. Okay? So what about just writing better R code? Okay? In general, loops are very slow. Apply, reduce, these functions people will often tell you to use because they're vectorized. People are liars. These are just for loops. You can look at the source code. They're just for loops. R level for loops. Map, lapply, sapply, mapply, and some of the other ones. These are not for loops. These are special things where some crafty people have done some black magic to try to shave off some interpreter overhead. So lapply may be much faster than a for loop. And for a large problem, that's generally true. The apply functions, however, are not what I would be willing to call vectorized. They try to shave off some interpreter overhead, but they're not really vectorized. Vectorized operation is, I have a vector x, like 1:10, right? X plus x, that's a vectorized operation. Okay? I didn't have to say for I and 1 to the length of the thing, It's just going to add everything together as though we have this high-level mathematical expression. Okay? That expression, by the way, would use the BLAS. But vectorization is very fast. Vectorization is basically custom C code that was designed to be very fast, C or Fortran code. It was designed to be very fast, but often consumes a lot of memory. Okay? So you can do your own kind of vectorization with plugging into a compiled language, basically. Speaking of compiled code, how would you do it in R? The easiest way is with this tool called RCPP. Remember, this is just a survey. We're going to have a breakout session. If you have particular questions about any of this stuff, we can go over as much as you like. There's also recordings of a much longer version where there's a lot more depth into these things. We're trying to pick up a little time. So RCPP is an interface to compiled code, and it's not the only way to interface to compiled code in R, but it's a nice one. It's not magic. It's not an automatic R to C++ converter, but it is a way to very easily write C++ code starting from your R code. And how might you do it? Here's a quick example. So we're in R, okay, and as a string, as character data, I'm going to store this C++ code. And what I'm going to do is there's some weird C++ boilerplate that you can't really get rid of, and I say int. So C++ functions have type. Say int +2, and it takes an int in. What do you think it's going to do? It's going to take in, and it's going to return in +2. Okay, simple function. With RCPP, this C++ code, we can very easily compile, link, load, wrap, bring into R. How do we do that? Library RCPP, source CPP, code equals this stuff here. And now, +2 is available to me as an R function. That name is available to me. So I can say +2 on 1, and it'll return 3. Pretty nice. So RCPP is great. I have a lot to say about that if you're interested. What about parallelism? This is parallelism. You have a problem, you put it on a CPU. Parallelism is you have a problem, you split it into subproblems, you put it onto multiple CPUs. And I'm being intentionally vague about what I mean by CPU, because hardware is really complicated these days. But this is what you want to see when you're doing parallel programming. Okay? This is what you want to see. You want to see, you're thinking about the resource and like the threads or the forks or whatever. You want to see things lined up very well with your hardware. Generally, that's not what happens. And it tends to look a little bit more like this. But ideally, you want to avoid this kind of picture. And in R, parallelism is very easy. First, just some terminology. Shared memory machines, these are bound by several thousand cores and maybe several terabytes of RAM. And you may say, oh my goodness, that's a lot. But, and a shared memory machine would be like your desktop, for example. But if you go to the distributed memory world, suddenly you have access to hundreds of thousands of cores and hundreds of terabytes of RAM. And so it's just a very different scale. So, you may have heard of this thing called BLAST, B-L-A-S-T. BLAST operates on these kinds of things for these really huge problems that I don't really understand the biology of. But, so just some terminology. Some shared memory packages in R. The parallel package, which ships with R as of, I think, 2.14 or so. So certainly you have it available now. There's SNO, which is ancient, stands for Simple Network of Workstations. For each, which I might have a lot to say about if we had time. GPU tools, HyperM, these are ways to access certain kinds of GPUs. So if you play video games, you can also use your computer to run scientific code. Kind of neat. In the distributed world, there's RMPI. There's also the stuff that I'm one of the developers of called PBDR. There's also stuff for the Hadoop ecosystem. I don't have almost anything nice to say about Hadoop. So if you want to hear about Hadoop, then oh boy, I got things to say. So distributed is like on your laptop, right? You don't have to worry about like where is something located. It's just on the laptop. But what if you wanted to use 2 laptops to solve a problem? Well, now you're having to communicate over a network. This is basically how distributed machines work. Just that network is very fast. That's the basic idea. There's lots more packages available on the CRAN HPC task view. Tons and tons of HPC packages available. This is a little bit of an overview of how things sort of link together in the hardware space. And it's kind of complicated. But you got the shared memory world where you've got like memory, a network. It's not that kind of network I just mentioned, but it is there. And you've got these things called cores, and the cores have these different cache levels. And what works there? Things like OpenMP, if you're in the compiled area, threads and forks, the multi-core package, the parallel package. Over in the distributed memory world, you've got basically multiple shared memory nodes connected over some kind of high-performance network, and they're all working together to solve a problem. Various packages for R will enable working in that kind of space in various ways. The world is complicated. We have these coprocessors. There's the GPU. There's also these things called Intel Mic, which you may have heard of. They're kind of neat. It's like a GPU, but slightly easier to program because nobody knows how to program GPUs. And then there's this stuff PBDR I'm one of the developers of, and we focus a lot on distributed stuff. So if you wanted to do like fitting a linear model on 50,000 cores of a supercomputer, well, we've done that. And I won't belabor the point, but that's sort of where we live. Anyway, quick wrap up. How should you be thinking about applying any of these ideas to solve a real problem? Okay, I haven't really shown you much, compressed for time, but the first thing you should be thinking is just get the stupid thing to work, right? The right answer you should be getting the right answer, whatever the right answer happens to mean. Once that happens, profile, using the profiling tools like rprof. Profile, profile, profile. Fix your bottlenecks. Maybe you don't have any, you can just quit. Probably you have some kind of bottleneck. Can you improve your R code? Can you get some free speed up? Can you bytecode compile? Will that help? Can you switch to a different version of the BLAS? Will that help? Build R with a different compiler? Will that help? Maybe they do, but not enough. So maybe try an lapply or vectorization, or maybe somebody's already solved your problem better than you have in a package. Try these kinds of things. Maybe not. Maybe you need to incorporate some compiled code with something like RCPP. And maybe that's not good enough, and so then you go parallel. Or you skip around and just try various combinations of these things. And just sort of keep going until it's fast enough that you're satisfied. Where to learn more? This is the book that I always recommend to people. Unfortunately, it's not like a free thing. You'd have to pay for it. And I don't like recommending those kinds of things to graduate students. But if you were going to buy a book, this is the one I recommend. This is what will teach you how to think. Norm Atloff is a computer scientist, I think at UC Davis, some UC school. And it'll teach you how to think about putting pieces of your programs together better. Let's put it that way. There's also R Inferno. This is free. It's written kind of strangely, like Dante's Inferno. I think it's sort of dumb, and they should just cut that crap out and just get to the point. But there's lots of really great advice in here, and it's free. Recommend everybody who uses R take a look at that. We also did a 4-hour tutorial containing this and much more in collaboration with NIMBioS. All the handouts and exercises and recordings of the event are available. And so when I make these slides available, you can click that link, and maybe you can find some interest there. Happy to take a few questions. We have some breakout sessions now or later. Okay,